Well, hello again. Dr. Bedgood here. We are now in week 5 of SCI101. We're going to talk about the simulation program that you're going to use for collecting your data for your scientific report. You'll find the intro to the simulation program that Dr. Schwartz updated, blended in with me speaking to you as well. But before we do that, I'd like to share my screen and make a few comments. I'm going to share this and do that. And I need to move this out of the way. Sorry, get my script. I've got the script so I don't forget to say anything to you. So now I'm going off script, so hopefully I won't. So as normal, if you come to the week 5 materials, you're going to find the, I don't usually look at it this way, but that's okay, the rationale, but most importantly, readings associated with this. And then here's the meat of it. So here's the PowerPoint for the lectures for this week. The lectures come in 2 parts. The first part, the introduction to the simulation model, and the second part, the simulation model and hypothesis testing. So this first part is going to be a blend of me and Dr. Schwartz talking you through the model and how to use it. The second part is about how to use Excel to do the statistics that you will need to do for your report. Let me just check. I said that. Okay, so let me jump to this. And we're just going to, Dr. Schwartz gives a good lecture on this. And then I'll make a few comments as we go.
So who has gone ahead and read anything about this disease model? One? And you mucked around with it for a little bit. You're using a PC, I notice, so you're able to run it. Did you run it online or did you download?
Oh, I ran it online.
You ran it online. Okay. All right, so there's a couple of options. Every year we have some issues because some people use Macs, some people use PC, some people use different browsers. I don't know what goes on. What we want to do is we want to run this disease model. The easiest way, if you can do it, is to run it online. But to do that, you're really going to need Windows Explorer. That's one of the drawbacks, because it runs on using Flash. There is something we can download if that's not your fancy, but we'll get to that in a moment. So if you're running this online using Windows Explorer, you may need to change your Java settings to allow that content from Shodor, S-H-O-D-O-R. That's the company that made this. So you'll be referencing this company. You can see that in your subject outline in your report. If you can't do it online, or you don't want to do it online, whatever, there is an option to download this program from NetLogo, and there's a model file, and I've got that on my computer, and I'll show you that as well. And there are instructions in the subject resource folder under assessment material on how to do that and how to run it. So I'm going to see if I can actually run this today, though, on... I don't think my laptop's got any access to the internet here, but let's have a look. If it doesn't, I'll try to run it from the other computer. Yeah, that's not going to work. It's really quite... Ooh. Maybe it is. So if I just go back to that, sorry. You'll see where I was there. That was in the subject site, where I just clicked on assessment number 5, scientific report, and I have all the relevant information for that assessment. And you can see that there's a link here to the disease model. You can also see how to reference this. And then there's instructions for how to use that disease model. And all of this is also in your subject outline. And we'll go through some of that shortly. Okay, so if you follow that link and it all works nicely, you should get to this page. Oh, sorry. You couldn't see any of what I was just talking about then, could you? Because I was using the other computer. And it works on Firefox as well? Awesome. So what I was just saying before was, if you go to your subject homepage and scientific report under assessments here, you can see there's the description of the assessment task, and we have a link to the show door model, and then there's how you reference it, and then there's a further description of how to actually use that model. So I've then clicked on this or copied that and pasted it into a...
So I have this updated, this you'll find, I'll show you this. This is the information for your assessment too.
New browser page, which is what I've just done, and I end up at this page. So here you can see we've got the show door, National Resource for Computational Science Education, disease epidemic model. All you should need to do here, now this might not work in Firefox if you try this. Click here to view the model, because this is the bit which doesn't always work, or the next bit perhaps. Okay, you got there, and how about open the model? Maybe they've changed things. But anyway, that's what you'll do, I hope.
So over the past several years, I've never heard from students that have had difficulty in accessing the show door model directly. So run it online without even bothering to download anything.
Well, yours is working. That's fantastic. Mine.
And it does take a little while to come up.
It's possible that, again, this computer in the lecture theatre doesn't have flash play.
I'm just zooming a bit.
Let me just... Okay, this... I want the next file. So we... There, you can use... There's more information on how to use this model. That information is still in your subject outline. So once you've got that going, and I can see some of you do, and I will show you again soon, you may want to, as you've done, Joseph, play around with it for a bit, but I've got some suggested starting parameters. So you'll see when you have your... Oh, hi. Okay. Yeah, okay. So you'll see that we've got a whole bunch of green people. You might have some other colours. So green people are people that will be susceptible to a disease. Red people are people that have already been infected. Blue people will be immune. And then white people are doctors, so they stand out quite quickly. That's not, it's just no particular colour coding, it's just how they stand out. Now with the doctors, this is important. So those doctors are treated as immune so that the medical care will always be available to the population. Doctors can give vaccinations and medication as long as you switch those options on in your disease model. And as I said, I have some suggested starting parameters which I think are quite useful. If we look at some of those others there, so susceptible, that's quite clear. The immune ones, so those people cannot catch the disease. They can either be immune because they were infected and recovered, they've been vaccinated, and you'll see them by holding yellow shields, or they've been medicated and they'll be holding pill bottles. Pardon me. So some suggested starting parameters are, and this picture I have here is, it looks slightly different now because they might have updated it a tiny bit, but we start off with an initial population of 2,000. You'll see that up the top. Top left? Yep. We're going to limit travel, so we want to keep it kind of simple. Not going to limit travel, sorry. We're going to turn travel off. So Joseph, I can see that you had travel limited, which meant you had a couple of bars, like walls. It's going to be like travelling between Mexico and the USA in years to come. You're going to have to go through barriers. So we want to keep that clear. We want to have people being able to interact with everybody. So we're going to have no barriers. It's an open society. Hygiene, a good suggested level, 20%. What sort of things are we talking about when we're talking about hygiene, do you think? These are sorts of things you'll need to consider when you're writing up.
Whether people wash their hands after the toilet, or wash their hands in general.
Yeah, whether people wash.
Showers, the kind of sort of thing you use.
Yeah, right. So personal hygiene, and that could be associated with food preparation as well. Yep. Medication I have off because I think that's kind of useful to just have that off. Infectiousness. So infectiousness is, well, I've got a setting there of 77, but does anyone know what infectiousness means? Yeah, chance of infection. How, if we had 100% infectiousness, then there's obviously, you guarantee people are going to get infected. That is not the same as fatality rate. Days to recover, I've got 96, so that's quite long. So a couple of these things you have a lot of space that you can play with, so you can change those variables quite a bit. And fatality rate, we've got 25%. Actually, that's pretty high. That's really high. Yeah. So we could, anyway, a number of doctors you decide. I suggest you have one doctor because you're going to have vaccinations on. Because, well, I suggest you'll probably have vaccinations on. Do I have it on? I've got vaccination on there, so I should have one doctor. If I don't have a doctor, then I'm not going to get those vaccinations out there. And what happens when you run it? And I'll try it. So the computer's still just not responding. Yes, so, well, it's just a time period. So you can see up on the top here that we've got ticks. So that's just an arbitrary measure of time, whether it's days, hours, something else. It's just a time measure. And what you're going to do is once you've set up your parameters, you're going to press, first of all, you start by pressing Setup Model. And then you're going to run that model. And you want to run it until everything stabilises. Or you can stop it after 5,000 ticks, whichever one comes first. So we'll run that simulation, like I said, until we get a steady state or 5,000 ticks. So we have a constant number. And you want, whatever you're doing, you need to be consistent because you're going to run this repeatedly to generate multiple repeat data sets. Once you've run that for a control, so your initial setup is going to be your control. Once you've run that for your control and recorded your data, you're going to then run that same thing for a treatment. And that will be where you just change one variable. Please don't change multiple variables because I don't teach you how to do analysis, ANOVAs, which is, or multivariate analysis. So just stick to one variable because that way we can see what is impacting upon the change, what is impacting upon the population. If you choose a single variable and you don't get anything interesting happening, you are more than welcome to choose another variable and change that. But please, when you're writing up your report, just address the one variable. All right, so before we get back into that bit of software running that simulation. I'll come back to it to actually run a few. We just want to go through a couple of concepts of infectious disease, because you need to be aware of these, because you're going to be considering them when you're doing this model and when you're writing up about the model. So firstly, an infectious disease is one that can be communicated from host to host, much like we do with measles, the flu, whatever. You have to come in some form, shape or form, contact with another host or a potential host. In our simulation model, we do not include airborne diseases. They have to come into contact. So your people in that model, your little green people, your susceptible people, have to actually come into contact with an infected person. What else? We're talking about the likelihood of becoming infected is dependent upon a whole bunch of different things. I'm sure you guys can think of some. I've just got a couple there. State of health, level of exposure, and the infectivity of the pathogen. Let's talk about what those are first. What's state of health? Yeah, how are we? So whenever we have a flu outbreak, something happening in our society, we always talk about, if you're, in particular, it's the elderly and the sick who are most susceptible. So that's a reality. We have to consider that. The state of health is going to influence your susceptibility. So if you're fit and strong and young, most times you'll be less susceptible. Anyone think of a case where that wasn't the case? An example where that wasn't the case? No, not so. I mean, that one's incredibly infectious and a pretty high fatality rate, so might be harder to see, but...
Are you after a specific disease, or...
Yeah. No, a specific disease. It was a while ago. So at the end of World War I, there was a huge outbreak of Spanish flu. And one of the odd things about that, I say odd because it was contrary to what normally happens, was that it was typically fit and healthy people that became infected. So that's, like I say, most cases it's the elderly or the sick or the incredibly young who are at most risk. Yes?
Was it because the men were from World War I? Is that why? Like they would have been
I don't know. I don't know the details of how it actually started. Albeit there would have been a heck of a lot of diseases and whatnot going on, simply because of the way wars were conducted back then, and there were so many injuries and so forth. I'm not really sure. You could look it up and find out. Okay, what else? Level of exposure. What's that referring to? So how much of the pathogen you're surrounded by or close to. So if you're working in a hospital, for example, and there was an epidemic, lots of people coming in, yep. Could also be how long you're exposed to it as well. So it can be not just the number of people, but it can be over a period of time. So we often talk about things as an acute or chronic exposure. Acute being relatively short, chronic being over time. That's normally for things that are toxic, but that's a concept of exposure. And then infectivity of pathogen. What about that? It's to do with that infectiousness, I think. Yeah, how effective it is at actually causing infection. And it has to overcome quite a few defences to actually infect someone. Do we have any natural defence mechanisms for disease? Our white blood cells, yep. Anything else? Yeah, exactly. Yep, so we have these physical barriers. We have our skin, we have fine hairs and multitudes of them in our nasal cavities and so on that help prevent infectious diseases from... That gives them something else they have to overcome to actually achieve an infection. Now, state of health, something we didn't talk about was, we mentioned elderly, we mentioned young, we mentioned sick. There's also prior exposure. So looking at it from the other way, if you've acquired some immunity, you're going to have a better defence mechanism. So we all know that when we get an immunisation, we actually, that is in a sense what we're doing. But if you've had measles, you're much less likely to get it again. If you've had chickenpox, you're much less likely to get it again. Innate immunity, we're not going to deal with that in this model, but that's where you cannot be infected. And then, yes, nutrition, lifestyle, stress, etc. They are all components of state of health. Our level of exposure. So the greater the exposure is equivalent to an increased chance of our infectious agent overwhelming the host and the host's immune system. So then we can start to consider these factors. We've kind of already touched on hygiene. What about medication? That can influence our exposure. It could be a positive or a negative, actually. So it might help impede depending on what the medication is, it might impede the infectiousness, or it might even make it easier to become infected. Our rapid or slow recovery of hosts, you're going to get to play around with that. The medication, in the terms of the model, I should say, the medication is actually meant to be one which helps prevent infection or prevent disease. But I was thinking, for example, if you were getting cancer treatment, that's going to be knocking around your immune system, so you become more susceptible. Where obviously this model is quite simple. It's not going to deal with those sorts of factors. It's just going to be, you're taking some medicine, let's say it's echinacea, bumps up your immune system. And then the number of infected hosts that can spread our infectious disease. Obviously, the more hosts there are, the greater the chance that you're going to get infected, the greater the chance you come into contact with someone who's infected. And in this model, if you come into contact with them, then I'll leave it there, because we're talking about infectiousness. So if you come into contact with someone that has that has the disease, and the infectiousness of 77 is quite high, then there's a really good chance you will become infected. Some of the other terms we need to think of are pathogenicity. So that's the ability of our organism to actually cause a disease. And that's dependent on a few factors, and we touched on those, like our skin, so the ways that they're transmitted. I'll skip on, because I want to get back to I want to get back to our model. But before I do, need to just say, do not confuse that pathogenicity with disease severity, because disease severity, pathogenicity is just how easily you are that you can get infected, but it might not be such a bad disease in terms of your overall health. So it might not be a particularly severe disease, even if it's incredibly infectious. So back to our model. We have our suggested parameters. What do we do then? We were talking about scientific method a couple of weeks ago. We need a hypothesis. So who wants to tell me what sort of hypothesis you might come up with? What have you been playing around with in here? Yep, so doing what? Okay, but let's talk about it in terms of this slide where we need a hypothesis. What did you try to do?
I was changing the ratio between days to recover and fatality rate.
You're changing the ratio of days to cover and fatality rate. Did you do that just by changing one of those variables?
Yeah, so
okay.
I left fatality rate at 50%, and if it took them like 10 days to recover, then they were all pretty much immune straight away. Or if it took them 100 days, then more die.
So let's take a step back. All right, you were changing the days to recover. So what's your research question and hypothesis?
Incubation period of the disease. It's not incubation
That's not incubation period. No.
What's that term called?
Well, let's just call it recovery rate.
Days to recover impact. Immunity.
health, maybe?
The
Impact of disease, health,
fatality rate.
fatality rate. All right, does it impact fatality rate? So can we turn that into a hypothesis?
Yeah. So say the higher number of days given to recover will lead to a higher fatality rate.
That's what you're asking. So do you think having a higher number of days to recover, so a longer recovery period, will be longer, will increase the fatality rate? Okay, so yep. So that's your hypothesis. So what's your null hypothesis?
So that's like the one where it doesn't, you don't have a cycle thing. So what's null hypothesis?
Basically, no, that's going to be almost another hypothesis. So she's saying, I think if I change the recovery rate to a longer period of time, what was your initial recovery rate? Days, time?
I think 32.
Okay, so you had an initial number of 32 days. So then you're saying if I increase that, I'm going to have a higher death rate. And that's your hypothesis. Your null hypothesis will be if I increase that, there's going to be no change. My fatality rate won't change. That's your null hypothesis, so nothing changes. And we need to come up with that hypothesis and null hypothesis, because when we're testing our data, when we're testing our model, and our mathematical model is what I'm talking about, more or less saying that days to recover won't have an impact. Yes?
I'm still stuck on why you have to write a null hypothesis.
Because it's the one we can test. So we can generate our data and we can test whether that null hypothesis holds true, but we cannot prove a hypothesis. It's just a scientific quirk. So we
already have those standard conditions. And
we can say something doesn't fit a model, so this doesn't hold true, so we can reject our null hypothesis, but we can't say, oh, there's a change, therefore that did change, therefore that's true. It's just one of those things I touched on earlier in the subject. We can choose to accept our hypothesis, but the more correct way of doing that would be to say we can reject our null hypothesis. So more often than not, we will talk about we'll talk about rejecting or cannot reject our null hypothesis. And that's just so that we're being a bit pedantic, I suppose, but it's just so that we're not trying to prove a hypothesis true, because we've stated that we can't do that. We just can't prove them true. You know what? Yeah, it's all to do with that falsifiability. So we can falsify a theory that we have or an assertion that we have. Yeah. So we need a hypothesis. By extension of that, we need a null hypothesis. Now, the reason we say need a hypothesis, you'll be able to come up with a hypothesis much more easily than a null hypothesis, because you'll have that research question. You say, this is what I think will happen. All right, so I'm going to make my hypothesis, and then you can say, all right, so my null hypothesis is just that will have no change. So, we've just come up with, or you've just come up with a good one, but this is where you should play around with it a little bit, because you want to develop, let's face it, you want to do something which you're actually going to see some results for. It's still valid science if nothing changes, don't get me wrong. But you're going to want to develop a hypothesis based on some sort of change. I suggest changing one of those only, but play around with it to see which one you want. You're not limited to that. You can change whatever you want, but I suggest one of those is probably a good one to choose, because the infectiousness of a disease, or its fatality rate, or its time to recover is going to, most likely, impact upon the health of that population. So pick one of those. Don't pick all three. And these are what we call our experimental factors. Like I said, just change one. So, we need to conduct replicate simulations. What do we mean? What do I mean?
So you do it multiple times so you increase your validity?
We do it multiple times, so yeah, you increase your validity, test the robustness of it, but we need to get some data that we can actually do some statistics on. When we did the chocolate experiment, did we just pick one person for each group and just go, you eat dark chocolate, you eat white chocolate, and look at the results? Because that could just mean anything. We picked as many as we could, which wasn't very many as it happened, but as many as we could. So you must do replicate simulations. You should do at least 10 simulations of each of the control and 10 simulations of your treatment. You can do more if you wish. They don't take that long to run, as we'll see shortly if I can get this working. By doing those replicates, we not only validate's not quite the right word, but we do investigate that robustness because we deal with randomness. And we also are able to then determine a mean and a standard deviation. And we need a mean and standard deviation. One, you're asked to determine the mean and standard deviation. What's the mean? What's another word we use for it? The average. Anyone know how to determine standard deviation?
How much is the average variance? How much like a fine?
Yeah, and it's based on the number of samples. Yep. Well, we can do that in Excel anyway, so you don't need to know the maths behind it. We'll be able to do it as a function in Excel, which we'll see at some point. And you're going to go on and do a t-test and then an f-test on your data. You're going to use Excel to do it, and Excel needs the mean and the standard deviation to do that. Now with the mean, we want that because, well, actually, who here has done any statistics? Anyone done any t-tests? No? I'm going to touch on it shortly. You have? A little bit. Do you know what a t-test examines? No. So we're going to use a t-test to look at the means of our control population and the mean of our test population. And that t-test is then going to be able to look at those two means and see if there's a significant difference. Or see if there's any real difference between the two. And in doing that, we'll be able to say, it looks like that our experimental factor does influence that health of the population. Or we'll be able to go, it appears to have no influence. And I'll show you how to do that in Excel in the second half of this lecture. It also helps us test for differences because, yes, we're looking at randomness and so on, but it gives us a better test of whether there's differences between the two groups. And as I said, at least 10 replicates for each group. Control versus experimental factor. All right, so hypotheses and, by extension, null hypothesis. As we already pointed out, the null hypothesis is that outcome will not be any different due to a change in our experimental factor. There'll be no change. And the hypothesis, which is the one most closely related to your research question, is going to be that the disease outcome is different due to whatever change in our experimental factor we came up with. When you're writing your report, you will typically put that in your last paragraph of your introduction. So you'll be talking about disease propagation in populations. You'll have a couple of examples maybe related to Ebola and so on. There's been quite a bit about Ebola over the last few years, so there'll be plenty of literature. You'll then say, and in this paper...
And of course, we've heard much more about COVID nowadays.
In this research, examining this hypothesis, it's effectively stating an aim. So in chemistry, we typically talk about aims. In science in general, we talk about hypothesis. You'll state your hypothesis, or no hypothesis, yeah?
So, like our essay introduction, like
The
background sort of.
Yep, so the introduction really does set it up as like a background, yep. And you'll mention literature that's out there, relevant literature that's been done on this sort of work. And it will identify why you're doing it. So it might be that we need models to help us come up with appropriate treatment for spread of disease or something. You'll find, I hope, some sort of literature to help you there to say that sort of stuff. But yeah, it sets up the scene. And we'll talk about the writing of a scientific report in one of the tutes, but basically you'll have your title. You can have an abstract. You don't have to worry about that so much in this report, but you might have an abstract, which is just a really brief summary. You then have an intro, which is background and why you're doing this work. And then at the end of it, you'll say, this is my hypothesis. Then you'll have materials and methods. So you'll talk about how you ran, you'll talk about the disease model and how you ran it. So you'll have some tables showing your initial parameters and your test parameters. And then you'll have a results and discussion section where you're discussing your results. And in that results and discussion section, you'll also use some literature to support your findings, your conclusions. All right, so before I get onto that, I want to see if I can get this model to work. Okay, so I'll take you
Here we go.
the showed all disease model that I've got. Now I'm using the NetLogo 6, and what I did was I also downloaded the infection file, as I said, and all you need to do is you go to, once you've opened your NetLogo, go to File, then Open, and you just need to locate the infection.nlogo file that you have. So I'll open that. Oops. I will open that. And you end up getting what you see on the screen here, where you have all of these little icons and slides and things on the left-hand side. So this is the model that's been set up for you. So this is the interface that you'll actually be working with. There is some other things that you're able to do, which I don't want you to do for this assignment, but you're allowed to play around with the code if you want. And there's also, if you look up top there, there's some info about about this model and what some of the parts in it mean. But I just want you to work with the interface. You can see we have a population number. The default is 1500. We are going to set this to 2000. I've just opened up on the right hand side the suggested settings, pardon me, that I have, and you might be able to see them here. I'll just zoom that in a little bit so that you can read it nice and easily. So I'm going to make this 2000. Number of doctors, I can leave it up to you as to how many doctors you really have. I'm going to have vaccination on. I'm going to suggest vaccination on. So let's have one doctor so that we can actually do vaccinations. Medication I'm going to have off. So we're not giving any medication. So vaccination on, medication off. Travel openings, I want no travel openings to start with. Now, of course, you may wish to actually see whether a travel opening, what that does for the spread of disease. I think that's probably something that's really interesting to see based on our current situation with COVID-19. Now, when I talk about COVID-19, if that's a bit too stressful for you, please realise you do not have to have anything. It does not have to do. Sorry, the way you set this model up does not have to have anything to do with COVID-19. You can set it up as whatever disease you want. It can be something completely made up, like the settings that I have in these suggested settings. They're completely made up. They're made up so that if you change some of these, you are likely to see some sort of result, which means our testing of the means should actually see something. So you should actually get some sort of result. Pardon me. So I'm going to leave travel openings off. I'm not going to limit the travel. You can see we have some boxes here that tell us how many healthy, infected, immune, how many people there are in our population, and the total number of people in the population, and then the total number that have died. See, we also have this color-coded, and you'll see a plot coming out on this curve later on. We also have some disease parameters. Now, infectiousness. This is set as a percentage. Often in the news these days you'll be hearing about infectiousness based on an R0 value. So we're not using this here. Now, the R0 value is the number of people that an infected person will actually infect. I think, I'll talk about COVID-19 again. I think the last I read it was something like an infected person on average will infect 2.6 people, something like that. I can't remember exactly off the top of my head. That is different to what we have here. So if we have infectiousness set at 100%, then 100% of the population will get infected. If we have it set at 50, then 50% of the population will get infected. And this infectiousness is something that we'll talk about a little bit in the lecture. I think it's in the current lecture. It's to do with, well, it's impacted by a number of things. So how aggressive the disease is. It's to do with whether it's able to bypass barriers. So the skin, for example, in your body is a really good barrier to infection. So it's to do with that ability of a virus to actually infect other people. So anyway, we want to set that to infection 77, so really very infectious. So, most of the population is going to get infected. Days to recover, we're going to set that to be really long. It's going to take a long time to recover. So that means people are going to be infectious for a long time and sick for a long time. Fatality rate, we're going to make that quite high as well, 25%. You can set these to anything you want, of course. These are just some suggested starting parameters. So once I've got those set up, I need to set up the model. So I'll press set up. You can see all of a sudden I have a whole bunch of green, healthy people. There should be 2,000 in my population grid there. And I've got one sick person. That's the red person. So that person is going to be infecting everyone they come into contact with. Almost everyone they come into contact with, because if we're set at 100%, obviously everyone gets infected. And the white person down here, that's our doctor. So they're going to immunise people that they come into contact with. Okay, so this is a fairly dense population. You can also see we've got some numbers up the top here. So total number of healthy, 1,998, because we have one infected person and we have one doctor. So now I want to run this speed a little bit faster. We're going to run this and we're going to time it for what's called number of ticks. Now, ticks are just an arbitrary measure of time in this case. So if the maximum amount of time you need to run this should be 5,000 ticks. If it gets to 5,000 ticks, just stop the simulation. What you'll be looking for, and you'll see it in a moment, is you'll see these curves going. What we're after is the curves to plateau and not change. So let's run it and see what happens. So you can see it's running quite slowly at the moment, so I might fast speed it up. You can see our number of infected people increasing, as to our number of immunised people. They've got a shield. Now, when these infected guys recover, they will become blue as well, because they will then be immune. You can see our numbers are changing. We now only have one healthy person, no healthy people, so actually everyone in the population has been infected, even though it's only a 77% infectiousness. So even though there was only a 77% chance that someone will get infected, really, because people are sick for so long and such a dense population, everyone's getting infected. We see these curves changing. When they plateau, our red, our sick line, we want that to remain unchanged, and our immune line, we want that to remain unchanged. And we've kind of reached that now. And you can see it's only got up to 1,000 ticks. So I could stop that now, but I might run it just a tiny bit longer. But I'll stop that at, say, or let's stop that now at just over, oh, so press it up. I meant to press stop. Let's speed it up again. Speeding that up, we'll go to about the same number of ticks, about 1,200. See how fast it's going. And I'm going to press run pause. So it's around 1,350 ticks. We have everyone immune, and we have a few people immunised. do record how many ticks you've got, because ideally when you repeat this, and you are going to repeat it, you're going to repeat it 10 times using the same starting parameters. Record the number of ticks it takes to reach that plateau. Record the number of healthy, record the number of infected, the number of immune, the total, and the died. And you're going to record that in Excel, and I'll show you that in a moment. And we're not going to change any of these variables just yet. We also have down here the number of people that have recovered. So 1,503 have recovered. We didn't have any medicated because we turned medication off, and we only had 14 vaccinated. So I'm now going to record those numbers in Excel. So I'll just open up Excel, and I'll bring that over here. And what you'll do is, this is my control. This is my control setup. I haven't changed any parameters yet. So these are my starting parameters, if you want to call them that. I'm going to do at minimum of 10 reps. And I'm going to record the number of healthy, the number that have died, the number that have recovered. I'm going to record the number that are immune. And these are the factors that I'm wanting to record. And I might even want to do the number of vaccinated. You may or may not want that. The ones that you definitely need will be healthy, the number that have died, and you may want the total as well. So here I'll go healthy, 0. Died, 482. Recovered. Now I should make sure that you can see this. I'll zoom in. Remember, this is our control treatment, or just control. I'm just going to zoom that over a little bit. Recovered is 1503. Immune was 1517. Vaccinated 14. So we're going to keep recording whatever data it is we need to record. You record it for each one, and totals 1518. I'm then going to repeat my run. I'm going to repeat it 10 times, or another 9 times. So I'll go back to my model, press model, and again. So this time it's running nice and quickly. Again, I'm going to wait until the curves plateau, or 5,000 ticks, whichever one comes first. And if they do plateau, I'm going to try to pause it at about the same number of times. So about the same time. So it was around 1,300 ticks. So I'm going to pause it now. Again, I'm going to record those numbers. You could also include an infected number there. I haven't got one. So healthy, we've got 0. Died, 482 again. Recovered, 1492. So we can see that that's different. Vaccinated, we can see that's different. Immune, 1517 again. Vaccinated was 25. And the total is 1518. We then do it again. Set up the model. You always have to set up the model. And we'll run it. Now, we are repeating it because you will get variation. We've already seen we've got some variation in our numbers, but you can get quite a bit of variation. I mean, these people on the screen are just walking around in random sort of directions. Okay, those have plateaued out again. It's around the same number of ticks. What are our numbers? I'm only going to do this last time, but you will obviously do this 10 times. 0 healthy, number of dies 485. The recovered is 1495. Immune 1514. Vaccinated 19. Now I have told you in the assessment description what variables you should record. I can go back to that in a moment. Total was 1515. And then of course you'll do that for the whole table. Now remember, you will also want to record a mean. So a mean is simply the average of all of these. So we can just put in average of brackets. Okay, we're going to go average all of those. So C3 to C12. And I'm going to just drag the cross. Now if you want the little trick, there's this little cross when you hover your mouse over the bottom right corner. That's going to copy the formula across all those columns, so I get the mean for all of them. always a good idea just to check. So if I click on that cell, it tells me it's doing an average of G3 to G12. So let's have a look. G3, yep, G3 down to G12. Excellent. So we get an average or a mean. We're also going to record a standard deviation because you have been asked to do that. You'll also get the standard deviation when you do the t-test, and I'm going to show you that in the second video. But you can do a standard deviation here because this is information that we're going to want as well. And again, you can do that using a function. So we'll go equals, and we can actually insert or search for a function. So let's look for a function. We're going to go for standard deviation. You'll find the standard deviation is one of the common ones. This is standard deviation of population. And that's fine, that's what we're looking at. So, but I was just going to type in, if there's nothing there, you can go to, just type in standard deviation. And you can see we get a few options. You can scroll down to see all the things you like. There we go, standard deviation, which is one I want. This function is available for compatibility with 2007. Estimates the standard deviation based on a sample, ignores logical values, etc. This standard deviation.p calculates standard deviation based on the entire population given as arguments. So you can use either of these two, it's not going to matter. I'll click on OK. It's then asking me for the range. My range is going to be our replications. We can copy that across and you'll see that we get a standard deviation for all of them. So that's how you'll use the model, and that's how you can record the data. You'll notice I've said here to, this is now looking at the information in the on the right hand side, information in the assessment. Record the number of healthy, the number infected, the number that are immune, the total, and the number that have died. And as I said, repeat that a minimum of 10 times. Okay, I'll now go back to the lecture, and then we'll go through a bit more about this, and then in the next lecture we'll actually go through, or the next recording, we'll actually go through the how you're going to do a statistical analysis of that data that you will generate.
So I'm just going to jump past a little bit here. So his saying the second lecture is exactly what the lecture is. That's where you will see he will go through the use of Excel to show you the stats that you're going to need to do. And I think this is where I want to be, right about here. And we'll just pick up from there.
Some data that I just whipped up in Excel based around that, different numbers to what we had the other day. So, but we can do some work on that using those numbers. And I've got some other numbers that I've also generated that we can use in a moment. But before we do that, just a little bit of theory. So, when we're looking at differences in based on treatments, we're looking at means. And these are population means or sample means. They do have different meaning. Whether you use sample mean or population mean does actually have a different meaning. I'm just going to use them interchangeably for now, okay? In context of SCI101, let's just say sample mean. So we have these two sample means. So we've got some sort of information response here from our first sample. Let's say that's our control. I don't know what the units are here. This is just made up, obviously. And then we have a second. So this will be our treatment, where our second data set. You can see our mean is the average of both our two treatments there, our control and our treatment. And we can actually compare whether those are different or not. Now we can also see that there's a little bit of overlap between our two data sets here. To me that looks like they're going to be different, but you know, maybe they are, maybe they're not. Generally speaking, we will use a statistical test t-test is the most common and probably one of the simpler ways to test the difference in means of two populations. So we'll use a t-test to test for those differences, and we can either do it for independent samples. In your case, your report, they will be independent samples, so those two samples are not related. There'll be paired, you could have paired samples. Now, a paired sample might be a before and after. So I could test all you guys, let's talk about the chocolate experiment. We'd have conduct the experiment on, just eating white chocolate. Then we could conduct the same experiment, the same people, after consuming dark chocolate and compare those two means. They would be paired, those two samples. In our case, we've got two populations, our control population and our treatment population. So they're going to be independent. And then finally, you could have one sample, which we won't be doing. I thought there should be more pictures coming up there. Anyway, the t-test will allow us to compare those two data sets, and we use it when we know that when the population mean and our standard deviation are unknown. Our population mean might be unknown because if you think about looking at populations, let's say we're doing it on the Australian population. You're not going to go out and test every single person. You're going to test a subset of that. So you don't know the true mean of the population. So we'll use a t-test there, and that there are assumptions that we'll be taking into account. We'll talk about that. So we'll use that t-test when our population mean and our standard deviation are unknown. And we have two independent or separate samples, so there's no definite relationship between those data points. And that's going to be the case for you guys. There's no definite relationship between your control population and your treatment population. The assumptions we're going to be making are that those two populations are in fact independent. I'm telling you they are, but we're making an assumption that they are. So you might want to include that in your report, that that is an assumption. You're assuming that your control and treatment are independent populations. We're assuming that our data will have that normal distribution, so that Gaussian curve that we saw. So those lovely symmetrical humps. And we're also assuming that the variance is the same between those two populations. We're assuming variance that's homogeneous. And when we go into Excel and look at that, we'll have an option of selecting a t-test, assuming equal variance, assuming unequal variance, and there's another one I can't think of off the top of my head. So that brings me back to the t-test. It's comparing two averages, two means, and it'll test for differences. So it's going to tell us how significant they are. We're going to use, I'll come to that in the next slide actually. Our measure of significance, I'll talk about in the next slide. But we're going to calculate a t-score, and that's our ratio between the differences, between those groups. You can also do it within the groups. And if we get a larger score, that's inferring that we get a greater difference between the groups. We can then look up a critical t-value, and we use a t-table to do that. You won't have to do that. You're going to do it in Excel. But you could, and I'll show you an example of that in a couple of slides. So our critical t-value, that is something which is the value that our t-score would have to exceed in order for us to reject our null hypothesis. What do I mean by that? If we're rejecting the null hypothesis, what does that mean? It means, yes, that's right. Yes, so if we can reject the null hypothesis, it means we are seeing some sort of change. So our hypothesis is that it changes, then we're seeing that change. Yep. All right. So we get a t-score, and we need to compare it to a critical t-value.
So that's looking at comparing the t-test using the critical t-value and the t-score. But as I've already mentioned in our lectures last week, we can also use our alpha value or a significance level and the probability value. So with our alpha value, we can pick a level. There's a few options we have. Typically, you go 0.1, sorry, 0.01, 0.025, 0.05. You don't often go much higher than that. So we often take a value, an alpha value of 0.05, which equates to 5%. And that significance level, or that alpha value, gives us a threshold for when we can reject the null hypothesis when it's actually true. So that's our 5% threshold for when we accept the fact that we can be rejecting our null hypothesis when it is actually true, so we shouldn't be rejecting it. So to put that in another way, we're saying we're okay with that scenario where, all right, if we make a mistake there, we're doing it, by accident, we're making what's called a type 1 error, but it's only going to happen 5% or less than 5% of the time. And we can evaluate that using our probability value, our p-value. And the probability of obtaining your data probability of obtaining data that's more extreme than your significance level, if the null hypothesis is true, is what your p-value is. So if our p-value is really small, less than 0.05 or less than 5%, then it is unlikely that we're going to be making an error and actually accepting or rejecting our null hypothesis when it's actually true. So we can express all of that fairly simply, and we look down at the bottom of the screen there. We can express it as our p-value, if it's greater than alpha. So let's say if our p-value is greater than 0.05, that is telling us we cannot reject our null hypothesis. It's telling us that the probability of us making that type 1 error is too great. So that probability of us actually making that mistake of thinking that the null hypothesis is not true when it actually is true is too great. So we cannot reject that null hypothesis. However, if our p-value is less than alpha, so in this case, if our p-value is less than 0.05, we should reject our null hypothesis. So that's telling us we're getting these significantly different scores, and the possibility of us actually being wrong about that is smaller than 5%. So we can reject our null hypothesis.
Who's seen a t-table before? Yeah. So if we get a t-score and we know what significance level we have, and we typically use alpha of 0.05, so 5%, we'd go, let's talk about, come on, mouse, I'm just going to talk about one tail. We've got these t-values here at different levels. I'd be doing, here we go, we want the 0.05, so this is one I'm interested in for the one tail. Here is our number of, oh, come on brain, just stopped, related to the number of samples, n minus 1 df. What am I thinking? That's our, that's our n minus 1 number. So if we have 10 samples, our df we'll be looking at is 9. So here we have to go across to 9 and 0.05, and we'd see that I have a critical t-value of 1.8. If my t-score is greater than that, then I can reject my null hypothesis. So we'll have two ways that we can look at it. All right. What's up? All right. So this is getting, I don't want to confuse you too much, so I'm going to go through it in an example. What I want you to remember is either, we're going to look at both really, but what you need to remember is if our t-score is greater than our critical value, we can reject our null hypothesis. Or if our p-value, the probability, is less than our significance, we can also reject the null hypothesis. And you'll get both of those. And I'm going to show you that next.
Value, which we can then
Good,
we can use our t-test table, or our t-table, to identify our t-critical value, which we can then see how our t-score compares against it. And as I said before, if our t-score is greater than our critical value, then we can reject our null hypothesis, which means we can then accept our alternative hypothesis. And also remember, if our p-value, so our probability value, if that is smaller than our significance value of alpha, which typically we use 0.05, then again we can reject our null hypothesis and then accept our alternative hypothesis. Now remember, I mentioned that t-tests, and as we'll see f-tests as well, they have several assumptions, and one of those assumptions is this normality of observations. That is that they fit a standard distribution, and that standard distribution is what we can see up on the top right-hand side. We're fairly familiar with this Gaussian type curve. Within that standard distribution, we have from the mean, you can go one standard deviation either way, and you have accounted for about, about 70% of your data. But of course, our data isn't always going to be normally distributed, and a good way of being able to look at our data to see if it is distributed normally or not is either using a histogram, as you see on the left, or a box plot. And a box plot, so this one that we have, the first one, that's for a normally distributed data set where you have a minimum value, first quartile, your median, which is the second quartile, then the third quartile, and then the maximum. And then you can have outliers outside of those. We can see the outliers down in this bottom one. This bottom one here, for this data set, shows you that it's actually not normally distributed. We've actually got a skewness of our data towards the right-hand side. And so we can use tests like kurtosis test to check for that, for skewness, or which is that lack of symmetry.
So I'll just say, in this class, you won't need to bother testing for normality of your samples.
And our kurtosis is really just a measure of whether that data is going to be heavy-tailed or whether it's light-tailed. So if it's a high kurtosis score, then it's heavy-tailed. Now, this is really beyond the scope of SCI101. If you go on and do more statistics, you'll get into this. And chi-square, again, is beyond the scope of SCI101, but chi-square tests really test for relationships, so independence of one group from another. So it can be sensitive to distribution and also to sample size, but we can use these to also, a chi-square test can also be used for goodness of fit. But anyway, we won't be talking any more about chi-square tests or kurtosis at this point, but I wanted to bring this up to emphasize that our t-test, as we mentioned before, makes that assumption of normal distribution. Now, a t-test is actually quite robust with that. So even if we're dealing with non-normal data, it will still stand up it's still quite rigorous, quite robust, I mean. So it still can generate some useful information.
Now, this is where we'll stop listening to Dr. Schwartz. Anything you see about F-tests, we will not bother with in SCI101. So I'm just going to get out of here. We are almost done. Let me close that. I realized I went off script, and so I got a bit ahead. I was going to say a few words before I showed all of that. So what you just watched will be in this recording. This is the recording that Dr. Schwartz mentioned, where he's going to do the statistics, actually show you how to do the hypothesis testing for some data using Excel. Now, let me go back to here. I wanted to show you So that's that. I wanted to show you two other bits of information. So if you come down here to great, it's not there. Okay, let me come here first. So your assessments, I'm still in student mode. So the information that's contained here, shoot, you can't see that. I apologize. Okay, let me get out of here and I will show you. Here we go, assignments. So here we go. This you will be able to read when it becomes available in the end of week 3, I believe it is. So here's the information. This is the same information that's in your subject outline. It's the task. This is the information about the simulation that Dr. Schwartz was talking about, how the program works. Healthy infected, he gives you a sample. All the information he already talked about is right here. Information about your report, how your report will be laid out. I'll make some more comments about that in a moment. The rationale and the rubrics, the rubric by which your report will be marked, and the form in which it should appear. I also want to show you, if we come to, sorry, I need to get out of here. If we come back to content and we scroll down, these things you can't see, but here's supporting resources for assessment 2. So here's another link to the disease model, and I'll just show you, I've opened this already. So this is what he showed you. Open the model, you click on that. It took a long time in his recording. It takes a long time for you to do this as well. It may take 5 or 10 minutes to come up. Shoot, I had this up and ready to go before I started recording this. We'll let that keep going. I'll come back to that. Hopefully it will come up. So here's a different link to the disease model. There's also a link from your assessment. I've got some questions that you might consider about spread of disease that could give you maybe some ideas about how to approach your experiment. Another discussion about how to do a t-test. I've already done 1 or 2 discussions of how to do a t-test when we were doing the chocolate experiment. Also, Dr. Schwartz is going through this on lecture 2 for week 5. And then here's another one of those. Here's some exemplar reports. So here's 2 good examples of work that your classmates have done in years past that have been quite good. And then if you happen to have problems running or accessing the show door disease model using Java, NetLogo for Macs and PCs, you probably will not need to do this at all. My experience the last couple of years is students just run it off of the internet once you stop waiting for it to start, and then you can run the program from here. So I believe that, let me stop sharing. Here we go, stop sharing. I don't want to share. Where did you go? Hold on just a moment, stop share. There we go, back to you. Let me just make sure, look at my notes here, make sure I haven't forgotten anything. Guide to writing in science, tutorial resources. The other thing I want to show you is here. If we come up to, the week 5 materials. So the reading to lecture I talked about. So here's a guide to writing in science. which may be useful to some of you in preparing your report. The tutorial for this week, for week 5, I would usually have a little bit of an introduction and go through these resources that we have to help you, to give you some information about writing your report. So scientific report writing, structure of a scientific report, 3 examples of introductions to give you ideas that you can have a look and see, hopefully, which you think is the better of these, as far to give you ideas about preparing your introduction. Laboratory report template. So this is something that's put out by the university. Need to download that. Here we go, by the Faculty of Science and Health, and gives you some ideas about how you might structure your report. We've already told you the way in which we want your report structured, so that may not be quite as useful. Discussions about writing an active and passive voice. So, because in this week, our tutorial, week 5, our tutorial is a guest speaker. We will not be doing this as a tutorial. And so consequently, I have a recording of when we did this tutorial as in the past, so that you can have someone walk you through these resources that we have available to help support you in writing your report. So this has been quite a long lecture. I apologize. That's the end. I hope you have a good day, and I'll see you at the tutorial this week. Thank you, with our guest speaker. Thank you. Bye-bye.